Ladies and gentlemen, welcome back. We are looking at Unit 5, and this is the example after our friction lab. So we have these new friction equations. How do they work? What are there going to be some other big pieces? We're going to talk about that right now. So in this example, we have a police officer arrives on the scene and sees this. We have a car that looks like it's skidded to a stop. So we have skid marks that last for about 25 meters. And as a police officer, you might want to be like, hold on, how fast was this car going before it came to a stop right now? So the police officer wants to know what initial velocity was it traveling, and all the other information that the officer knows was, here is my coefficient of kinetic friction. Just to let you know, if you want to go back here, this is rubber on road. We have rubber on dry asphalt. You can see between 0.5 and 0.8. So we're just going to use 0.6 as being our situation in this, just to make it a little interesting. So we're going to go through and solve this problem. As always, with all... Actually, you know what? Why don't you guys try to solve this problem? It'll be really interesting to see if anyone can walk away with it. I'll give you a hint right now. Notice how the mass of the car is unknown. Whenever you run into this situation, I always say just try your best, see what you can do with the things that are given to you, and you will see that there's a little trick that we can use in order to solve this problem. Pause it, give it a shot. Alright, so in this situation, what I would do is I would list off all the things that I have in Unit 3, all the things that I have in Unit 4, and pray to goodness graciousness that somehow I can relate both Unit 3 and Unit 4 using my famous equation, A equals net force divided by the mass of the system. So right away I come into this and I'm like, okay, I really need to get the acceleration. Can I get the acceleration? No. I know that I have delta x is equaling 25 meters, which is great. And I know my final velocity is 0 meters per second. So you realize that what I'm really looking for is A. If I can get A, I can get his initial velocity. So A is my main target. Notice how I don't have any more information, so guess what? I probably have to go into Unit 4. Unit 4 tells me I should probably draw a force diagram for this situation. Let us start there. So force diagram for this car while it is stopping, we have Fg on the car by Earth, and we have Fn on the car by the road, and we have the frictional force going in the opposite of the motion, Ffk on the car by the road. So that is one piece in my Unit 4 knowledge. The other piece that I can start to see from this is I notice right away that my net force is equal to Ffk. The other thing that I would probably write down if I was in this situation is my new Ffk equation. Notice that my new Ffk equation is mu sub k times Fn. If I wanted to dig a little bit deeper, you will see that I can also write this mu sub k, and notice how Fn is equal to Fg in this situation. And I know that Fg is written as 9.8 newtons per kilogram times the mass. So I really have this equation that I've kind of dug really deep to find is equal to mu sub k times 9.8 newtons per kilogram times mass. And so all what I've done is I've written this as mass, right? I can actually plug in for my mu sub k because I do know that. That is 0.6, so that is something that I know. And so really, I have an equation that has mass in it. Well, I want you to realize something that's really nice and easy about this. If I were to take this equation and plug it in here, I probably will do a whole bunch of fist pumps, and you'll see why. So let me just do that really quickly down here. I have A is equal to, let's actually do this, 0.6, which is my coefficient, does not have any units on it, 9.8 newtons per kilogram there, and mass. And I have on the bottom of this equation mass. And you realize that I can cancel out the masses, and my acceleration is just 0.6 times 9.8. So right away, I can solve for the acceleration. And as I said before, if I can get the acceleration, I can go back on over here. I will have then 3 knowns, and then I can solve for my initial velocity. So you will see that this problem really evolves based upon my new equation. So I'm going to ask you guys to actually go through the math, figure out the initial velocity, and tell me, is that fast? Fast or not? Think about it, solve for it, and we will discuss that tomorrow. But to recap this example problem, I just want you to realize how easy these problems can be. Number 1, if you do whatever we do in Unit 3 and Unit 4 and connect them together through this equation, you will be golden. That's number 1. Number 2, you will note that in certain circumstances, you might not know the mass. As you can see, I did not know the mass. I did not panic, though. All what I did was I wrote it as m. And then what you do is you pray that when you plug in the net force equation up into this mass of the system, or net force over mass of the system, that mass will cancel and you will not have to actually know the mass, as we can see in this circumstance. So we will get some more practice on this in worksheet number 2. Just know that that is a trick that you can use. You can write it down algebraically, m, and then hope that it will cancel when you actually go into your acceleration equation. All right, I'll see you guys tomorrow.